Good afternoon, and thank you for joining us for the 2019 Annual Technology Baseline webinar. We're coming to you here from the National Renewable Energy Laboratory. Before we dive into the heart of this, we just have a few quick webinar logistics to get through. This webinar is being recorded, and we will be posting it to the NREL YouTube channel in about a week or two. So if you want to go back and review it later, you will have that opportunity. If anybody is having audio issues, we suggest trying to switch from your computer audio over to your phone audio. If problems still persist after that, GoToWebinar Help is probably your best bet to get it resolved. We will be taking questions at the end of this webinar. So if you have a question at any point, feel free to submit it using the questions panel in the GoToWebinar interface on the right side of your screen. And we will answer as many of those questions as we can with the time available at the end of the webinar. So with that, I will turn it over to Laura, who is going to be our first presenter.
Hello, everyone. This is Laura Vimmerstead. I'm the lead for the Annual Technology Baseline, and I work with a wonderful group of individual technology analysts from the National Renewable Energy Lab and from Oak Ridge National Laboratory. Their names are listed here. Today, we'll be covering an overview of the Annual Technology Baseline, cost and performance comparisons, technology-specific highlights where the folks from the whole team will address those, and a preview of the standard scenarios report. Let's get started with the overview of the ATB. So the ATB documents a transparent and consistent set of data that supports analysis sponsored by the Department of Energy, Energy Efficiency and Renewable Energy Office, and is made available publicly to other analysts. In addition to, so ATB is widely used in NREL analysis across a variety of analytic products. And in addition, it's used by a whole variety of other parties for a variety of analytic purposes. A major use at NREL is in the standard scenarios report. And my colleague Wesley Cole will offer a standard scenarios preview at the end of this presentation. So the ATB includes 4 different products. The core spreadsheet offers the data and the calculations. The web application documents the spreadsheet, and this year, for the first time, we also have a Tableau workbook and formatted data set to provide the data in a more structured way. So the ATB includes capital expenditure, operations and maintenance, and capacity factor data for the base year of 2017 with projections through 2050. And these are all used to calculate a levelized cost of energy for each financial assumption scenario. So we have 3 different technology scenarios and 2 financial scenarios. The technologies covered are shown here. We provide our own national laboratory curated estimates for the renewable energy technologies, and then for completeness, we include EIA data for the conventional technologies. The process of the methodology to develop these estimates includes 3 steps that are shown here, and I'll walk through each of these in turn, from defining the resource bins, developing the cost and performance data, and then calculating the LCOE. So this slide shows the technologies and resource bin categories that we highlight in the Annual Technology Baseline. And these have been fairly stable between last year and this year. There were more changes in the previous year. As an example, so this is a land-based wind supply curve, which shows the capacity factor associated with different quality of research, or of resource rather. And we highlight TRG4 in our summary slides and in most of the summary charts on the website. But the other TRGs are also available in the data. And then for even more detail on resource, there are other products beyond the ATB that can be used to look at highly specific resource data. So in the second step, we develop cost and performance data for 3 different technology cost scenarios with base year 2017 this year and projections to 2050. So these are the constant, mid, and low technology cost case. This slide summarizes the sources of the base year data, which is now 2017. And generally speaking, the main change in terms of sources of base year data is that several of our technology programs are using more bottom-up cost modeling in developing these, which is also the case in terms of our sources of projections. So that's probably the big change in terms of sourcing between last year and this year. In step 3 of our data development, we take a bunch of financial assumptions and use those along with the capacity factor, Capex, and O&M to calculate a levelized cost of energy. And it's important to note that the LCOE is a summary metric that has important limitations. So our documentation discusses that in more detail. So now I'll turn to the summary of 2019 ATB technology cost and performance. So this is mainly housekeeping changes from last year to this year. We did come out with the new products, as I mentioned previously. In terms of more substantive updates between last year and this year, this slide provides an overview of those, which the technology analysts will be going into more detail about. And as I mentioned before, several of the methodological changes now use bottom-up cost modeling, which really reflects that we're seeing changes in technology markets as well as additional R&D advances that are best reflected in those bottom-up models. So the next few slides are comparisons of the major parameters across the different technologies for the year 2030. And this is just a small sampling of the data that's available in the ATB. So we provide the full time series data. We show comparative charts for several different years, and all of the data is available for downloading in both the spreadsheet form and CSV form and as Tableau. So you know, if the chart that you're most interested in is not one of the summary charts shown here, there are lots of ways that you can access and visualize the data. So we have the Capex comparison here, capacity factor comparisons for 2030, LCOE, as I mentioned, important to consider the caveats and limitations of the LCOE and to understand what goes into this. We do include the R&D effects on technology cost in this R&D financial assumptions case, and then we have a second financial case for calculating LCOE that includes the market effects as well. So this slide shows the sensitivity to those two financial cases. So the market case here is adding on changes in the background rates, like interest rates, taxes, to contrast that with the R&D only case. So this year we did add back in a cost recovery period equal to the technical life of the technology. And so this slide reflects the three different cost recovery periods of 20 years, 30 years, and technical life. So as a default, the 30-year life is used. So I'd like to turn now to the technology-specific highlights, starting off with Tyler Staley with LandBased Wind. Again, this is an overview of the comparison of the R&D financials in 2018 versus 2019. So the next few slides with the individual technology analysts will give you a sense of what has changed between last year and this year. So, Tyler.
Yes, thank you, Laura.
Thanks.
Okay, so for land-based wind specifically, to get the projected cost and performance estimates from the basis year out to 2030, we carried out an expert assessment to see what turbine technologies look like in 2030. Some examples of primary turbine characteristics include plate capacity, rotor diameter, hub height, and this was done for the high innovation case or low cost, and the likely or mid case. So after defining these representative 2030 turbine characteristics, we conducted a bottom-up cost analysis using a suite of the systems engineering tools here at NREL to estimate the cost and performance for the mid and low cases. Since turbine characteristics become more difficult to predict the further out into the future we go, we shifted from a bottom-up approach to a learning curve methodology, which was informed by historical data to estimate the cost beyond 2030. As done annually for the ATB, we also conducted a literature review to inform and verify the projections. These projections methods were updated from the 2018 ATB, primarily informed by the expert elicitation work on future wind energy costs published in Nature Energy in 2016. This was done for a few reasons. First, the expert elicitation is now starting to become dated. So the survey was conducted about 5 years ago, and since then, larger turbines and new science-based innovations have been introduced into the industry. Also, the updated methodologies tend to be better aligned with the recent market trends, showing cost reductions attributed to turbine scaling, with additional cost reductions from various innovations, such as advanced controls. We also see improvement in turbine design and reliability and more efficient O&M practices as well. Additionally, the bottom-up modeling approach enables better understanding of how specific innovations and technologies may impact future wind plant energy costs. Next slide, please. So here's a graphic that depicts the LCOE projections of land-based wind for the 2018 and 2019 ATB overlaid, specifically for the TRG4 under the R&D financing options. The shift for the constant case is a result of updating the basis year from 2016 to 2017 and aligning the 2017 costs with the annual cost of energy review that NREL puts out. For the mid case, we see a steeper cost reduction trajectory from the basis year out to 2030. This is from the shift to the updated bottom-up cost modeling methodology for the 2030 estimates. And beyond 2030, the learning curve methodology results in a similar reduction trend to that presented in the 2018 ATB. The low case results show a similar cost projection to that of the low case in 2018 ATB, despite the updated projection methods in this year's ATB. So with that, I'll pass it over to Philip to cover the offshore wind slides.
Thank you, Tyler. So turning to offshore wind, so in order to derive cost and performance values for the 15 techno-resource groups for offshore wind, we've exercised a spatial cost model, which has allowed us to estimate the levelized cost of energy and the composite cost components at more than 7,000 sites. TOGs 1 through 5 are intended to represent fixed bottom substructures, and TOGs 6 through 15 represent floating offshore wind technology. We've classified TOG 3 as representative of near to medium term installations in the United States. For the base year, we've implemented a number of updates compared to last year's ATB. These include lowering the turbine Capex in the base year from around $1,500 per kilowatt to $1,300 based on market data. We've also lowered the export system cable costs by around a fourth based on market intelligence suggesting a decrease in costs due to supply chain competition and a change in the material use and commodity pricing. And then we've also included, and this is a cost increase, a higher price for offshore wind lease area prices based on information that became available through the lease sales in the northeast of the United States. And we've included a market with 25% on the contingency level side above European contingency levels. In terms of the projections into the future, that is reliant on an expert elicitation conducted by BVG Associates and some other literature. We're using that to inform our mid case, which is intended to represent a 50% probability for realization. The low case was informed by expert assessment of looking at some technology pathways and R&D advances, where we've doubled the rate of reduction compared to the mid case. Some general words on what justifies the reduction in costs that I'll be showing on the next slide. So we have seen, informed by market trends both in Europe and in the US, we're seeing decreasing costs, primarily driven by larger turbine ratings up to 15 megawatts in the early 2030s. There's also increasing competition, especially in European markets, that we think will translate to some extent to the US markets. We're seeing increasing economies of scale in production and in installation and O&M, improved siting and better understanding of the resource, and innovative control design and material supply chains. Similar to what Tyler mentioned for the land-based side, we've updated our expert elicitation, which was based on an assessment conducted in 2016. We've updated that to a more recent literature. And then an additional effort that's noteworthy here is that the price information that's been released through the Vineyard Wind Power Purchase Agreement, the first commercial scale project in the United States, has allowed us to validate some of our price and cost data that we've obtained for the US market. Next slide, please. So on this slide here, we can see the last year's ATB base year and projections compared to this year's. As I've mentioned, we're estimating a clear decline of costs compared from last year's ATB, starting for TG3 at around $100 per megawatt hour in 2017 to around $50 or $50 in the 2030, 2032 timeline, and then decreasing in the mid case to around just above $30 out in 2050. And I'll turn it over to the next speaker.
Great. Thank you so much, Philip, and thank you, Tyler. I just want to remind everyone on the phone that you can submit questions using the question panel in the GoToMeeting interface. And we we'll look forward to answering your questions at the end. Next, I'll turn it over to Dave Feldman to address the solar PV projections.
Thanks so much, Laura. Thanks everyone for attending. I'm going to review PV. We have three different types: utility scale, commercial, and residential. In each of these cases, we represent 5 different capacity factors, looking at 5 different locations around the U.S. Sort of high, medium, low, and sort of the medium, high, and medium, low. The just indicative or mid case is so, for example, for utility scale PV, which is have a capacity factor of 20%. That 20% is actually lower than the median of current U.S. installations in the field, indicating that currently, right now, there are places that are more PV is going into sunnier places than sort of the average. But that's our base case is more sort of the average than the average for what's going in. I should also note that capacity factors that we include, include the degradation over time, and then also the DC to AC conversion. I think PV is unique in that we still, when we're quoting things in the ATB, we still use the DC rating, which I know some of the industry does not use. With regards to our projection methods, similar to how we've done historically, and a little bit different from some of the other technologies, we do a literature survey. In this year's case, we had 25 different projections from 10 different institutions for all 3 markets, but in the case of utility, we had 11 projections for 9 institutions. The mid case is based off of the median of those projections. The low case is the lower bound of those projections. And there's linear interpretations because often projections are not every year. Sometimes they're every 5 years or every 10 years or things like that. So we have to do a little bit of cleaning there. We also only use projections for domestic projections, so projections for what will happen in the U.S. Through 2030, and then afterwards we include global projections because we feel that currently there are reasons that the U.S. market is above the global average, and by global I don't mean sort of talking about the developed countries as well. But by 2030 we feel like things like the ITC will no longer be relevant. That will be increasing reported cost of prices. We also adjust all of these projections for single axis because that's what we're representing, at least for the utility scale. Our projections, we feel like there's a lot of justification behind. While we do use the literature survey, we feel like there's a lot of justification behind those projections. First of all, if we just look at the recent PPA prices that have been awarded, but not for projects that haven't been constructed, they indicate further price declines. If we look at the module cost reduction opportunities, which include efficiency improvements and production line throughput improvements, that we've seen both announcements from companies where their official roadmaps for the next few years, but also looking further out, I should say. And then looking really far out and maybe towards the lower case, we've seen a lot of newer technologies that offer novel semiconductor type things. There's also further more improvements of economies of scale or cost manufacturing locations. So there's a lot of reasons that the module will both get lower costs, and improve efficiency, and that efficiency will also help the balance of system opportunities. So the more efficient panel, the parts that go around it have to be, there are fewer parts. There are less panels, fewer panels. There's also opportunities for improved racking systems, supply chain optimization, inverter improvements, and just improvements in the installation process. So we've updated our literature review. There was concern or sort of questions about our base year data last year. We've updated that. We historically, previous years, have been using a reported pricing, average reported pricing for the base year, and then switching over to more of a bottoms-up benchmark. And we've shifted really towards, for our base year, we now also use the bottom-up benchmark to be more consistent with other technologies and also our forward projections. Our updated pricing reflects higher inverter loading ratios. With that, maybe to the next slide. So if you'll see, there's, I guess there are two things to note. If you look at or a few things to note. The constant case, there was a dip in the constant case, and it went back up, and that was in the past year. We took into account the tariff impact on module price, and we have taken that out this year because we feel like there are many other macro factors that are affecting the price of the module and a PV system, so we didn't want to isolate that. And we felt like a lot of the projections that we were using to base our estimates on had already baked in that tariff anyway. So so you'll see that price is relatively constant. For the mid case, somewhat higher than past year. So if we look at just really the 2030 and 2050 estimates, they're fairly similar. We had different different literature to base our estimates on, and similar for the load projection. Pretty much by 2030, 2050, they're pretty much the same. It's really just the early years where, again, we had a different set of literature, so we had different numbers. With that, I will turn it over to Parthiv, I believe.
Thanks, Dave.
Thank you, David. Parthiv Kurup here. I'm going to be speaking about concentrating solar power. And, I'll start off with the technology representation. It is still currently a molten salt tower with 10 hours of storage, and that's representative of Crescent Dunes in the US. That is likely to change next year, but for now it's sticking. It's important to highlight that there are three main resource classes, which are where we would expect some CSP to be built, which include Daggett, California at excellent, Phoenix, Arizona at good, and Abilene, Texas as fair. With the NSRDB, or the National Solar Radiation Database, which is included in the System Advisor model, downloaded from sam.gov, you can find that the capacity factor is actually increasing from 50 to 64% based on where you would put that plant. It's worthwhile highlighting that the projection method has been improved and changed for this year. So the literature survey has now 13 projections from 7 different institutions, and these have been specifically selected going out to 2030 and to 2050, which showcase that the costs of tower technology are potentially reducing. And that's what the MID is based on. And then there is also a report which came out in 2019, which showcases how some of the global costs of CSP have been converted to the US market. It's worth highlighting that the low originates from a IRENA 2025 estimate, as well as DOE research targets for high temperature advanced CSP. As we move forward in time, we are seeing movements already in terms of large plants. We're seeing improvements in terms of financing and efficiency gains. We're also seeing much better supply chains in place, and then helping to drive some of that cost reduction in the future. It's worth highlighting that these general improvements include financing improvements as well as changes in PPAs. So, for example, in the global markets, there are certain large plants being built today which have 35-year PPAs, which are very long for a concentrating solar power plant, but could become more used in the future going forward. It's worth highlighting, as in the notes, that the Las Vegas, Nevada location as the good has been replaced with Phoenix, Arizona, mainly because it's more likely to have build in Arizona. And it's also worth highlighting that the resource classes have actually improved in the NSRDB, the National Solar Radiation Database. Next slide, please. Here we can see the levelized cost of energy from 2017 out to 2050, where the black is 2019 data and green is 2018 data, again for Daggett, which is class 5. And then you can see the low, mid, and high and constant projections. As can be seen, the 2019 mid has improved in terms of LCOE, and that's because of a improvement in the Capex projections, where, for example, by 2050, the levelized cost of CSP for electricity could be around $58 per megawatt hour in California, compared to last year, which was about $70 per megawatt hour. And the last slide for CSP is regarding the Capex, which shows the 2019 and 2018 comparison. It's worth highlighting that the 2021 start point in the ATB is created through detailed bottom-up as well as survey of the industry, which is now reflected as a US dollar per meter squared and also other costs specifically for CSP in the system advisor model. Then the mid projection is created using other projections found in literature. And what's really interesting is that, for example, in today's world where a 2020 plant or 2021 plant, which is coming online, is actually at around $6,500 dollars per kilowatt. For example, the NOR 3 plant, which is actually very similar to what we are projecting in ATB today, and then going out to 2030, you can see that the cost projection is at around $4,800 per kilowatt, which is actually, again, very similar to today's very large Dewa plant being built in Dubai, which is for 700 megawatts, and that's at around $5,500 per kilowatt. So the projections are pretty close to industry, and we will keep refining in time. Thank you very much. I'll switch over to Chad.
Thank you, Parthiv. Next up, we have Chad Augustine presenting geothermal, and I'd just like to encourage folks to continue to submit questions using the question panel of the GoToWebinar. Chad? You might be on mute. So Chad, we're having trouble hearing you if you're speaking. Okay. So we're going to skip to Hydropower with Debo Oladosu from Oak Ridge National Lab. Debo, are you on the line?
Yes, thank you.
Thank you.
So on hydropower, the technology representation is tied to the type of resource, and this is because of the fact that costs and performance at hydropower sites are firmly tied to the kind of resource, and there's a lot of variation. So for this purpose, we've divided the hydropower resource into two categories, and then into four sizes under each of those, based on the dam size or head and the potential capacity at each site. In terms of the projection methods, these are based on a comprehensive analysis that was done around 2016. We're making an effort to update that, but we have not done that yet. So for this year, the projections are essentially the same, but the scenarios were based on what was developed for what's referred to as the hydropower vision study. And the low technology cost case represents advanced technology, and the mid technology case is based on a reference from a NEM simulation at that point. The justification, especially for the low technology cost case, include implementing a series of innovations in engineering, design, construction, including what's referred to here as drop-in systems, which can be better termed now as standardized modular systems. Also, alternative materials, optimization using information systems, developing turbines that avoid environmental impacts, and improving the permitting, licensing, and approval process. So these are the justifications for the vision for low technology cost for hydropower going into the future. As I mentioned, the comprehensive study on which this was based has not been fully updated yet, and so most of the projections are the same. And so what we have done mainly this 2019 is to update the inflation rate to move the cost to 2017 base year, using inflation rate on cost components as well as construction for hydropower. So the next slide. And so most of the costs have not changed much comparing 2018 to 2019 in terms of the LCOE. The constant estimate is flat, and it's about at $50 per megawatt hour, and the mid-range is declines slowly onto 2050. The advanced technology case, where if we are able to successfully implement those technology options that I highlighted in the previous slide, we hope then that will drop costs by up to $20 per megawatt hour. So those are the highlights for hydropower.
Thank you, Debo. Next up, we have Wesley Cole addressing storage, and then we'll try to pick up Chad Augustine regarding geothermal.
Okay, thanks, Laura. So we have battery storage. It was the first time we've included it was last year, so we've updated the numbers this year. So our technology that we're representing for battery storage is a 4-hour lithium-ion battery, 15-year lifetime, utility scale. We don't have any distribution scale or behind-the-meter costs for battery storage included. The projection methodology was based purely on literature reviews, so we surveyed the literature. There's now a lot of activity in the space. There was a lot more out there than there was before. So over 25 projection, pulled those together and used that to create our low and high cost projections for utility scale storage. So there's been a lot of activity in this space. There's been a lot of cost reductions, especially looking at the literature from 2017 to 2018. There was major reductions in estimated costs. So if you want to go to the next slide. So the costs relative to what they were last year are now shown. You could see the starting point is a lot lower. That's due to recent cost reductions. And one of the reasons why it was great that we were able to update this. And you could now see what the projections look like. The reduction amounts in relative terms aren't that much greater, but you're starting from a much lower starting point to get those. So that's all I would say there. You want to?
Do you want to address this question right now?
About including why we didn't include.
So the question about what, so if I'm understanding this question, it's why aren't we doing any connection with storage and PV together? So there's a lot of activity around hybrid systems where you could couple a PV plant with a storage plant. There's some tax credit benefits currently with the ITC, the investment tax credit. And there could also be some other cost savings depending if you're going to couple it behind the inverter, in front of the, depending on how you want to situate it. We didn't put that in the ATB this year. There's a lot of activity going on in that space, both at NREL and elsewhere. That might be part of what is in the next year's ATB, but currently we don't have any of those coupled systems in this year's report.
Great. Thank you, Wesley. So next up, Chad Augustine addressing geothermal.
Okay, thanks. Yeah, for geothermal, we had a big update this year. The Geothermal Technologies Office published their geothermal vision study, or GeoVision study, and we used the data and analysis from that study to update inputs for geothermal into the ATB. In terms of technologies, the ATB assumes two types of geothermal technologies. More conventional hydrothermal technologies, that's what exists now, that's what people are used to seeing. Those are the existing plants that are built from naturally occurring hydrothermal systems, such as like wherever you see geysers or hot springs. And also it includes enhanced geothermal systems, or EGS, which is a technology where the reservoir is artificially created or made, and then the surface looks just like a conventional hydrothermal plant in terms of the technology. For each of those, there are two types of surface technology. There's a flash plant, which uses either direct steam or generates steam from a steam hot water mixture from a turbine, or a binary plant, which is an organic ranking cycle. For the geothermal resources, we developed a site-specific resource estimate for those locations where we had site-specific data, and this included the identified hydrothermal resources as identified by the USGS. And then for other locations, other resources such as EGS resources, we used representative sites for those to make projections of what they might cost to develop them. In terms of the projection methods, we incorporated a bottom-up analysis that's outlined in the geothermal vision study, that includes estimates and justifications for all of the various costs and technology components, such as exploration costs, drilling costs, power plant costs, and O&M. And these cost projections, or these costs, were developed in conjunction with the other national laboratories by discussions and through discussions with experts, and were validated by an industry team that we called our visionary team. One of the scenarios that we have in the GeoVision study is a technology improvement scenario, and that assumes, or that cost will be reduced by a combination of improvements in exploration, reductions in drilling costs, and the ability to use EGS techniques both at conventional hydrothermal plants and at EGS locations to greatly reduce the risk of developing geothermal reservoirs. If you could go on to the next slide, please. All right, so this is the projections for the levelized cost of electricity for both 2018 and 2019. This assumes just one of the four scenarios, a hydrothermal resource which is the conventional resource that uses a flash plant at the surface. In the low scenario, costs are constant and there's not much to talk about there. In the mid-case scenario, we assume just a constant learning rate and a relatively low learning rate over the lifetime. And this is to reflect that hydrothermal technologies are a relatively mature technology. They've been around since the 1960s, and we just expect incremental decreases in costs. The low scenario incorporates the assumptions from the GeoVision technology improvement scenario. And even though those mainly focus on improvements in enhanced geothermal systems or EGS technologies, those advances cross over into the hydrothermal technologies to show the hydrothermal resources to lower their costs as well. So improvements in exploration and reductions in drilling costs for EGS also help hydrothermal systems. The hydrothermal systems also benefit because they're able to use EGS techniques to take wells that previously would have been dry and turn them into useful, productive wells. And finally, the thing that's driving down costs in the low scenario is because of that risk reduction in developing wells and developing reservoirs, the overall risk of the project is reduced, which lowers the weighted average cost of capital for geothermal projects and helps to push the LCOE down in the low scenario.
Chad, before we leave geothermal, there was a question on the line about possibilities of induced seismicity from EGS systems. Do you want to take that now or later?
I can do it now. Yeah, there is any time that you're changing stress states in the subsurface, there is the possibility of induced seismicity. In fact, for a successful EGS project, there has to be induced seismicity. There has to be some sort of fracture creation. Usually, these events are very low in terms of in magnitude, like usually so small on the Richter scale that they're imperceptible to humans. There have been cases where there are larger induced seismic events that can be felt by humans, and the Geothermal Technologies Office has developed a induced seismicity protocol to be followed for developing EGS projects, so that when induced seismicity beyond what is normal or safe is observed, steps can be taken to curtail it.
Great, thank you. So next up, we have a standard scenarios preview from Wesley Cole.
Great, thanks, Laura. So, the reason we're talking about standard scenarios here is a couple of reasons. One, just from our background, these products used to be coupled; they would come out together. We've now decoupled them just for a variety of internal reasons. But the standard scenarios are now the projections of how the grid will evolve using these annual technology baseline costs. So what you've seen here today are just cost to performance projections. They don't say anything about how competitive these technologies will be or how they might be deployed or where they might be deployed. So the standard scenarios are the companion product to the annual technology baseline that then use NREL modeling tools to create projections for the evolution of the U.S. power system that take in all these input cost performance data as well as all your geographic constraints and transmission and load shapes and all those different pieces, put them together and do a least cost optimization modeling to project how the grid will evolve over time. So there's a variety of scenarios that are included in the standard scenarios. At least one thing we've learned a long time ago is that any one scenario is always wrong. So looking at ranges of scenarios we found to be very helpful. So you could see the different scenarios that we're planning on running this year. I think there's 42 of them up here in their various combinations. They touch on a wide range of things. you could see that technology cost box is drawing from this annual technology baseline. So you'll have these low and high costs that are taking from the low and the constant or high case projection from this annual technology baseline, and then running them through our models to see how a deployment is impacted. So next slide. So the standard scenarios is a suite of scenarios. Accompanying those scenarios is a report that highlights various areas of change. Those areas are listed here. So this year we're planning on looking at cost and value of natural gas and renewable energy technologies, firm capacity, how the various state level mandates and renewable energy standards are impacting generation mix, and then just different how generation mix trends are evolving across different parts of the country. So we've typically published these in October. It varies. There's a lengthy review process here, but that's when we anticipate the report and scenarios to be published. So with the report, we put all the scenarios online. So we have this standard scenarios results here. You could go there to see what they were last year. They include state level results by technology and have various other outputs. So you could go, click on the little cloud button, it'll pull the data down. So that's available there to try and to share the modeling work we've done. You could then look at, well, with these cost to performance projections for these technologies, here's how things could evolve over time.
Great. Thank you, Wesley. While you're talking, I'm going to roll into some questions about battery storage. And we had a question about why the units are in dollars per kilowatt hour. We had a question about a $130, I'm sorry, in kilowatt hours, not kilowatts, $130 per kilowatt hour manufacturing, and about the role of recycling of batteries in considering what the Capex might be. So those
these are all great questions. So so these are 4-hour duration batteries. So you could go from this $1 per kilowatt hour or $1 per kilowatt to $1 per kilowatt hour by just dividing by 4, and that gives you $1 per kilowatt hour cost. We just showed it this way because all the other technologies are in $1 per kilowatt terms. We want to be consistent, and certainly if you're competing this against a gas turbine, that's one thing. So there's a lot of ways to look at this. We're just using dollars per kilowatt to be consistent with other technologies, but it's pretty simple to convert between them. In terms of, I think important for this as well as for all other technologies, the costs that we're using for the ATB are like a cost for 2020 is the online that represents a system coming online in that year, rather than a cost that's ordered that year or a PPA assigned for that year. So when you're looking at these costs versus other things, you want to keep that in mind, and that these are meant to be all in costs or overnight costs, but all in there.
Next up, we have a question about some of the modeling for land-based wind, the bottom-up modeling. Tyler, did you want to go ahead? The question is, what made the costs go down, and what the contrast was with the 2018 methodology, and what was the difference between 2018 and 2019?
Yeah, so this year's ATB used the bottom-up cost modeling, and that is an artifact that brought down the cost compared to last year's. So what we selected for this year's is one of many technology pathways to get to an endpoint in the future. This happens to be one that we've selected for this year's ATB, and it would indeed be different from last year's projections, since those were more of a top-down elicitation results from that expert survey conducted in, the survey was conducted in 2014, and then the results published in 2016. So that is the sole reason that you're seeing the drop in costs. With our ability to define the turbine characteristics, say out in 2030, for rotor diameters, hub heights, and the scaling of the turbines, we're able to run these exact characteristics models, obtain more accurate costs, and predict better energy production for each of the scenarios, the low, mid, and high.
Okay, thanks, Tyler. Next up, we have a couple of questions about solar PV for Dave Feldman. And Dave, there was a question on the line about the LCOE, whether that was in DC or AC, and then another question about the inverter size used for the DC calculation, I guess.
Sure. So when we do LCOE, well, because the Capex and the O&M and the capacity factors are all in DC, but the capacity factor is DC per. Basically, the short answer is it's an AC. It's in the energy that's results that is produced by the systems that either goes to the grid or to a person's home, which is currently we just assume it goes through the inverter, which converts DC to AC. So I guess it's after the inverter and therefore AC. Sorry, long answer, but AC. And then I think I'm not quite sure I can read the whole thing on my screen, but the question is what was the inverter loading ratio assumed? Was that the question, or I can't quite read the whole question in the question thing. Laura, do you know what the? Sorry.
Okay, it says since costs are on $1 per kilowatt DC, is the DC value based on inverter size or the total PV panel capacity?
Right. Yeah.
And also, if you could comment on the inverter load ratio.
Sure. So we assume when we do talk about capacity that when we talk about capacity in terms of watts DC, we're talking about the standard test conditions of the module, the panels, so in DC. And when we talk about AC, we're really talking about the inverter capacity, which is rated in AC terms. So modules DC, inverter AC, and so the inverter loading ratio has an impact on that, and we have different inverter loading ratios depending on the market. So I believe that our ILR for utility scale is 1.3, and I believe in cases where we needed to do that, and I'm not sure whether we did, but needed to convert for AC is 1.15, but that really wouldn't come up unless we were converting some sort of projection or something where we needed to make that conversion. As far as the actual, right, I guess it would come up with the capacity factors. So for the capacity factors, those are the things we're assuming. But for the standard scenarios, they have a whole other set of assumptions. I mean, they also, that's an input there that wouldn't be in the ATP.
Great. Thanks for those clarifications, Dave. We have a set of questions about tower construction, which I think apply to CSP as well as both onshore and offshore wind. So there's interest in the specifics of how those towers are constructed. And Parthiv, would you like to go ahead and field that?
The question is, how sensitive is the cost of the tower to the construction method, and what construction method did you assume for these towers?
That's a good question, and realistically there is a specific tower cost formula in SAM, the System Advisor Model, and that's based on today's technologies, not things like additively constructed towers. So it's based on empirical data from real plants that were constructed, and then you have a formula which effectively scales based on the height that you request and based on the power that you need for your site. So the bigger your site, typically the taller, but you can change that. But the tower construction method is the standard block addition method with concrete and reinforced steel. How sensitive? It is fairly sensitive once the height starts increasing significantly beyond 200 meters.
There was also a question about the causes of the decrease in cost for CSP.
I'm just trying to.
From last year.
Right. So what reduction? So I'll just repeat the question so that people can see Jakob's question. What reductions drive CSP costs down, the mirror storage, turbines, and so on? So my answer is, in the large-scale plants, there are many cost reduction levers. Those include large supply contracts, which are being created now for these mega plants being seen in the MENA region of 700-800 megawatts in one go. Another is improvements in assembly and reduction in site assembly. Another is actually a finance lever, which is the use of lower cost debt, plus also longer term PPAs, so 30 and 35-year PPAs instead of 20 and 25-year, like in parts of South Africa. Yes, there has been some improvements. So we show the improvements in the power block because of areas like, for the power block, we actually have used something called the Chemical Engineering Plant Consumer Index, and that's for specific items such as heat exchangers, steam turbines, and so on. And that, in the last couple of years, has actually reduced in cost. So that's been another lever. All of those details can be found in the recently released report from Craig Turchi and the rest of the team from the NREL site. But those are some of the big levers we're seeing right now. Thank you.
Great. Thanks, Parthiv. I wonder if Tyler or Philip would like to address any aspects of tower construction.
Well, as far as the land-based side, we're assuming typical steel tower construction. However, as we go taller in hub height, we have to introduce new types of technology, such as segmented tower bases to fit under current infrastructure in the U.S. For the construction. Those costs, we've tried our best to capture them in the cost modeling, the physics-based cost modeling, for including transportation of those tower segments, and then also the construction on-site of those taller towers. So more or less, these cost impacts are baked into the results in the ATB values and cost estimates.
Okay. And there was a question about alternatives to steel towers.
There is research going on and actually projects that utilize concrete towers, and more and more research and development is going on in that area to see if there's any further cost reductions that the industry can utilize in that area. There are historical lattice towers as well that have been looked at, and there doesn't seem to be much more activity in that technology currently.
So I'll give the individual technology analysts a bit of a break here and address some of the questions about the ATB. This presentation will be published online within the ATB website. There was a question about the data for the Tableau files, and the CSV files contain all the data that's in the packaged Tableau workbook that we are distributing. So those CSV files can be used as folks wish. And there was also a question about the dollars. So those are 2017 dollars that we use throughout the ATB, real dollars for 2017. And I think we've answered many of the questions. If folks have more questions on the line, please go ahead and submit those.
We did have one question, general question about the 30-year life for resources and why that was.
Oh, yeah. So there was a question about why we use the 30-year cost recovery period. And so previously we had used a 20-year cost recovery period. Based on some of the things our technology analysts were seeing, we did switch to a 30-year cost recovery period. And I wonder if Tyler and Dave would like to address that. Dave, do you want to go first?
Sure. I mean, I'm not sure. I guess the 30 years is I'm trying to think. Sorry. How to best answer that?
Hey, Dave. Tyler will go ahead.
Yeah. So the current understanding, or in the past, recently, turbine technology has been in the 20 to 25 year range, and now we're seeing manufacturers pushing the envelope to the 30 and even 40 year range, and we're seeing OEMs getting certification for their turbines to last this long. So it's important to introduce this type of analysis into the ATB in order to capture some of these results on LCOE by extending the life of these wind plant projects. I know in the Wind Technologies office, we're looking more into extending plant life, and this is kind of a fruitful area that there might be a lot of benefit for these wind plants to continue operating with some residual value and their impact to levelized cost.
Yeah, and part of the question was also noting that IPP investors might expect capital recovery after 10 years. So if you or Dave want to address that as well.
So there are multiple investors when you think about a renewable energy project. And while certain investors expect returns at a certain point, so for example, debt might only span over 7 years or 15 years or whatever it is. The question is, how long is the sort of the total asset? How much do all investors expect these things to go forward? And there's a lot of sponsor equity that really are counting on that residual value that Tyler's talking about. And while certain investors really want to get their return after by the time that a PPA hits, a lot of folks are expecting there to be continued value after that. In fact, we just published a paper recently this year talking about how there really is, for most technologies, significant value after 30 years. And it's really about O&M practices and other things that you can really extend the life. So I think we're pretty comfortable with 30 years, given sort of how the financiers think about recouping their costs.
Sounds good. Thank you. We have had a similar question come in on the line about the assumed life of battery storage. Wesley, did you want to field that one?
Yeah, so our assumed lifetime is, again, largely based on literature, and so we're using 15 years. It varies, so we're assuming 1 cycle a day for our typical battery performance. Battery technologies range widely based on how you design it, what chemistry you're using. So certainly, like, you could find shorter, longer lifetimes. You could operate it differently to get different lifetimes. You won't find that kind of detail in the ATB, but hopefully that gives you a sense of what we've chosen to represent.
Great. Thank you, Wesley. One more question on batteries coming in.
So asking about potential for flow batteries versus lithium-ion. You've seen our representative batteries is lithium-ion. There's a lot of activities, and there's also other storage types. You've got pumped hydro, you've got compressed air energy storage, you have flow batteries. There's a lot of types out there. We're not attempting to be comprehensive in any way. Lithium-ion has been the dominant technology deployed recently and appears to be over the near future. farther than that, it's hard to say what will happen. We haven't weighed in there at all in the ATB, but that could potentially come down the road.
There's a question on ultra-high pressure for hot applications. I wonder if the person asking that question could clarify which technology he's referring to. And there are some other questions about specifics, like requests for some of the references and publications, and we will follow up with those offline. There was also a question about where to find the CSV files that are visualized in the Tableau workbook. And on the annual technology baseline data page, there's a place where it says download the 2019 ATB summary. And that's the area that should have both the Tableau, or no, sorry, that has, I think it has all of the CSV files as well as the Tableau workbook there. So if you poke around in that annual technology baseline data area of the website, you should be able to find those. And if not, please contact me, Laura Bimmerstead.
I think we're getting down to the end of the questions here. If anybody else has a question you'd like to submit, go ahead and add it now in the next minute or so, and otherwise I think we'll wrap up.
What's this paper that we published on investment?
I think that came in while Tyler was talking.
Okay.
There was a question about a publication on investment, and if you want to go ahead and clarify which paper you're referring to, that would help. Otherwise, we'll follow up offline. And with that, unless we get any other late-breaking questions here real quick, I would like to thank everyone for joining us today. And please don't hesitate to contact us with questions or feedback about the annual technology baseline. We're always looking for ways to make this product more helpful to everybody. Late-breaking question about whether a hydrogen fuel cell study is being added. So every year we kind of take stock of where we are and what needs to be added to update the ATB and what we can do within our scope and budget. And so we are considering a variety of future directions. I don't have a specific plan today about adding a hydrogen fuel cell study. There certainly are studies of hydrogen and fuel cell elsewhere within NREL's and DOE, EERE's publications and ongoing projects. So that's definitely an important area of research. I think, I guess we did have a question about ultra-high pressure performance concrete for hot applications. Parthiv, did you want to take that?
I can. As long as the question is relative to use of concrete for thermal energy storage and very high temperatures. Currently, that application space is being researched. It's not yet an area which has commercial technology at greater than 600 degrees Celsius, but it's not unfeasible. It's just it has to be researched further.
So with that, I think that we are wrapping up the 2019 Annual Technology Baseline webinar, and thanks everyone for attending today. And again, please don't hesitate to let us know any questions or comments beyond what we were able to answer today. Thank you, everyone.
Thank you.